Hello, everyone, and welcome to this lecture on Python for scientific computing and data science. My name is Chris Myers. I'm in the Center for Advanced Computing at Cornell. As was just posted on the last slide, if you have questions, please put them into the chat, and my colleague, Chris Cameron, will be helping me moderate those questions. So again, welcome. I'm glad you're able to join us on this cold and snowy morning. By way of outline, I'm going to begin with a kind of an overview of the Python ecosystem for scientific computing and data science. And then I'm going to spend most of my time kind of diving into a few core packages, NumPy, SciPy, and Pandas, and showing some of their capabilities. And then finally, I'll sort of wrap up by talking a little bit more about how this whole ecosystem is integrated amongst itself. By way of resources, so I gave a previous lecture last semester on an introduction to Python, so that was more about the programming languages and some of the basics, and if you're still coming up to speed with Python, you might want to revisit that. There's also a lot of good documentation, including a tutorial on the python.org website. As far as these packages that I'm going to be talking about today, NumPy, SciPy, and Pandas, there's really a lot of excellent documentation on those websites describing different functionalities and use cases. And then in our Cornell virtual workshop materials at the CAC, we have several different topics, tutorials on different aspects of Python that are related to today's talk. I just want to briefly summarize some of the features of Python as a programming language, and I talked about this more in my last introductory lecture, but it's sort of relevant for what we're going to be discussing here today. So Python is a general purpose programming language. So unlike some other languages you might have used for scientific computing, it wasn't originally developed specifically for scientific computing. It's also an interpreted programming language, so it's not compiled at its core, but and so intrinsically, it can be slower than compiled languages, but that is offset by the fact that Python is also an extensible programming language, which means that we can extend it with compiled modules within the interpreter. There's this Python C application programming interface, this API, that lets chunks of code be written in some other language and compiled and then callable from Python. And so in fact, most of the functionality for scientific and computing and data science is not in the core language itself, but it's provided by third-party libraries, which are often implemented using these kind of extension modules to have numerically intensive parts running in compile code rather than interpreted code. And in fact, the scientific computing community was an early adopter of Python for a number of reasons, but has played a key role over the years in helping to develop tools to assist with developing interfaces to different numerical libraries that are useful for scientific computing. There's more information in an appendix at the end here, so I won't really go into much detail about, but given that these packages that you would be using are not part of the core language and library itself, you would end up installing typically additional packages to support your work in scientific computing. And this can be done in a number of different ways, but typically and often as sort of best practice involves creating customized virtual environments that install packages that you like. And again, more of that is discussed at the end in an appendix. So this is kind of a schematic overview of, at least from my perspective, of what at least part of this Python ecosystem looks like. At the core, we have the Python programming language and this Python C API that lets us build extension modules. And then the Python standard library is something that comes within every installation of Python and provides a lot of useful functionality. NumPy is this very important package that I'll be talking about, which really is kind of the basis of a lot of the rest of this ecosystem. And in fact, in the talk today, I'll be focusing, as I said, on NumPy and a couple of other important packages for scientific computing and data analysis. But really, this whole ecosystem kind of builds from the bottom up to create increasingly complicated functionality for different kinds of problem domains. I won't be saying a lot about data visualization today, but next month, as part of this series, I'll be giving another lecture in this series on Python for data visualization, where I'm focused more on these particular packages and what they can do. So I'll start now with NumPy, which is short for numerical Python, and this is really the cornerstone of the scientific computing ecosystem. It's largely written in the C programming language and has links to the BLAS and LAPACK libraries that provide functionality for linear algebra. And it's at its core, it provides support for multi-dimensional arrays plus linear algebra and random numbers. Sorry. My slide, there we go. So the core data structure that is provided by NumPy are these multi-dimensional arrays, or ND arrays, n-dimensional arrays as they're referred to internally. And what these arrays provide is both the ability to construct arrays, but then also a rich array syntax that enables complex expressions and efficient computations. And I'll describe in more detail what that looks like. And so this, not only does this provide this sort of array syntax, but these arrays really then form a substrate for lots of different kinds of computations that use arrays throughout this whole ecosystem. And NumPy arrays are similar in spirit to the role that arrays and matrices play in MATLAB. And in fact, there's this useful page that's part of the NumPy documentation that introduces NumPy for MATLAB users. So if you're familiar using MATLAB and you're trying to port to NumPy, there's lots of useful information about how to do that kind of migration. The picture at the bottom here is just sort of sketching out what I call the anatomy of an array. So an array can have, again, it's a multi-dimensional array, and the axes of an array describe the order of the indexing into the array. So axis equals 0 is sort of the rows of an array, axis is one of the columns, but of course there can be more than 2 axes. And the shape of an array is a Python tuple that indicates the number of elements along each dimension. So this array here has shape 8, 3, and that's a useful attribute to be able to access. Unlike a Python list, a NumPy array essentially is homogeneous in data type. So in this array that I've sketched over on the left, these are all of D type, data type int, but generally, there is a homogeneity of type for any particular array, except in certain special cases. And you can combine through different operations. Arrays constructed from items of mixed D type will be upcast. So if I add an int array and a float array, I'll get float arrays because that's a greater common type. So within NumPy, I can do a variety of things. I can create arrays, for example, and this is all I forgot to mention. This is all running live in a Jupyter notebook here. So I can, for example, import NumPy as NP, and this naming, this is a conventional shorthand when we import a NumPy array, is to shorten the name NumPy to NP so that we don't have to type as much. And so, for example, I can explicitly create an array from a list of numbers, a Python list of lists, and I get some array X, and then I can ask what its shape is. Its shape is 3, 3, as you can see. There's also functionality for creating arrays algorithmically. So, for example, I can create an array, a 3 by 3 array of random numbers, of uniformly distributed random numbers on the unit interval. Or I can create, for example, an array of linearly spaced floating point numbers from 0 to 1 at some density. So an important aspect of NumPy arrays is to be able to access elements in those arrays. And this uses Python indexing and slicing, basically extending the syntax that is there for Python lists, extending that to multiple dimensions. And so just as a reminder, indexing in Python, counting starts at 0, and negative indices actually refer to counting back from the end of an array. And slicing allows us to access ranges of elements where we start at some starting value and end before some stopping value. So I can create some different array A, and for example, if I want to access a particular element of that, A1, 2 will be the axis 0 is the rows, so it's row 1, column 2, and that's this element 7 here. Similarly, if I just want to return an entire row, I can just provide a single index here and get this entire row number 1. Or if I want to slice out a subblock, this slice from 0 to 2, 0 to 2 gives me this upper left-hand corner of the array that might be useful for some particular computation I want to do. So just remind you, there's A. If I leave off indices in the slicing, I basically, so if I leave off the stop, it basically slices to the end of the array. So this is a subarray that starts at this element 7 and then slices this lower right-hand corner. If I leave off a beginning slice, it starts from the beginning of the array. And if I leave off both the start and the end, I essentially slice out entire rows or columns. So in this case, this returns column number 2, although not as a column vector. So I think that this is a different kind of behavior than you would see in MATLAB. That this, if you wanted to treat this essentially as a column vector, you would need to reshape it as such. And then, as I said, there's negative indexing. So, for example, if I wanted to slice out the last 2 columns of this array, rather than having to compute, what the shape was and figure out where that is, I can count from the back. And so this slice here from -2 to the end slices out these last 2 columns. So slicing is useful not just for being able to access elements, but we can even set elements by slicing assignments. And so, for example, I can create this 8x8 random matrix, but then maybe for some particular computation, I want to zero out everything on the boundaries. Well, I can do that basically just with these 4 slice assignments for the 0th row, the last row, the 0th column, and the last column. And then you can see what W is there. These examples that I was showing were all for 2-dimensional arrays, but of course, these are n-dimensional arrays that we can support. So, for example, here's an array Z that is a 3-dimensional array of shape 3, 8, 2. And if I, for example, wanted to slice out the back face of this, I could do something like this slicing here, picking out the last entry in the 3rd dimension, and then that would return this 3x8 array that is that back face. So it's very useful to understand all this kind of indexing and slicing syntax so that you can manipulate these arrays in various ways. There's a number of very useful array operations within NumPy. So there are element-wise unary operations. So these are operations that act on a single array, and these are also known as universal functions or ufuncs. So if I want to exponentiate every element of some array A, I can call np.exp, and that'll do that in an element-wise fashion, take log, sines, cosines, lots of different mathematical operations. And these all produce a new array of the same shape with each element transformed by the applied operation. Similarly, there are element-wise binary operations, so I can add 2 arrays with the plus operator, subtract arrays, multiply, divide, exponentiate, etc. As well as these arithmetic operations, I can also execute binary logical operations on arrays, and we'll see an example of that. So importantly, these arithmetic operations are element-wise. So if you're used to MATLAB and having, for example, the times operator referring to matrix multiplication, that's not what's happening here. If you actually want to do a matrix multiplication or some kind of dot product, you can use this add operator, for example, to do a matrix vector multiply and using the tenets of linear algebra. There are a number of aggregating unary operations that I'll show some examples of, where we can do operations optionally along some specified axis. And then there are lots of functions for different kinds of array manipulations to reshape and bundle things together in different ways. As I said, we have these element-wise array operations. And so for example, I previously defined 2 arrays X and Y, which are of the same shape. And therefore, if I want to, for example, create a new array W, which is 3 times every element of X minus 4 times every element of Y, then I can do that with this simple operation here. I can execute logical operations on this. So I can ask, for example, show me everywhere, or to execute the operation W greater than 10, and that then returns an array of the same shape as W, but filled with trues and falses with Boolean variables, depending on whether or not those elements are greater than 10. And then that operation forms the basis of this very useful function, np.where, where I can say, for example, everywhere where w is greater than 10, fill it in with whatever the value of w is, otherwise fill it in with 0. And this is just one example of how to use that. But again, using these different kinds of operations, I can manipulate arrays very, very efficiently. So as I said, I can add, I can add arrays. And so, for example, I can define two big random arrays A and B, and I can create a new one by adding them element-wise. But let's go ahead and actually run that and in the process time it. So I'm using here this time it magic function in IPython and Jupyter that tells me how long it'll take to run this cell, and it'll take a little bit. So to run this, it ran it a bunch of times, and on average, it took 833 microseconds to execute this command, C equals A plus B for these 1,000 by 1,000 matrices. If I were to do this explicitly with for loops in Python, which is sort of how you might think about it initially, I would do something like this. I'd first have to check that they're the same shape, because otherwise it doesn't make sense to add them. I would have to create some array C that I'm going to put the contents in, and then I would loop over all of the indices I and j in both dimensions to do something like this. And if I were to time this, it'll run a little bit. It takes approximately 202 milliseconds per operation. So if I were to see how much of a speed up I got there, I could do 202 times 10 to the minus 3 divided by 833 times 10 to the minus 6. And I got a speed up in the first operation of approximately 242 times. So not only is this array syntax much more compact, but it's also more numerically efficient. And the reason that is essentially sort of sketched out here, that this NumPy is one of these compiled extension modules. But if I write out a bunch of operations with for loops, such as I've done here, then every time I want to access an array element, I need to sort of dip down into this extension module, get a value, bring it back up to Python. I'm doing all the looping, I'm doing all the indexing and the addition in Python. And so I'm spending a lot of time jumping back and forth between Python and the compiled extension module. Whereas when I say C equals A plus B, there's essentially only a single call, which is encoded in this plus operator, where I dive down into the extension module, and all of the looping, all of the addition, the indexing is done within the extension module, and then a value is returned. And so the overall runtime of this is much shorter than in the case where I've done this looping. So these array operations represent a kind of a form of vectorization. They can be, and in fact, can be ported to other backends that support vectorization, such as, say, if you've got GPUs, there are NumPy implementations on GPUs that use that as a backend. And the conventional wisdom here is basically to avoid these kind of for loops in Python when you're working with NumPy arrays, and use this array syntax using these aggregate array operations for better performance. The challenge in doing this is to figure out how to express very complex operations only using this array syntax. So adding two arrays is very straightforward, but in some cases you want to do some complicated set of things, and the challenge is to figure out how to do that. And you can use these various techniques with indexes and slices, and another technique known as broadcasting that I won't really go into here. But the challenge, the goal is to try to figure out how to do that so you're not explicitly writing for loops and accessing subsets of the data. Sorry, I've got a question here. Do both of these options copy your array to a temporary object, or is it operating in the original object directly? Well, I guess I'm not sure. When I create the array C in this C equals A plus B, there is a new array that is created. I mean, it has to exist, and so in that case, it's not temporary in the sense that I've created this thing. But it's an excellent question, because as my point down below in the bullet points is, one of the caveats of this is that this convenient array syntax can sometimes disguise some performance efficiencies, because it does in fact generate temporary arrays. And I'll give an example of that. And if I don't really fully answer the question, please let's go back to that. Interestingly, there are alternative approaches in packages like Python and NumPy that encourage you to unroll these loops and to write explicit loops, but that's because they use additional compiler technology and generate extension modules essentially, and they can in fact generate more efficient code if the loops are explicitly written out. And so depending on your performance needs, you might actually want to look into something like that. I won't say more about it here, but in our CVW on Python for high performance, we kind of address that in more detail. I mentioned that there's a kind of aggregating operation. So for example, I have this array X, and if there's a method on an array sum, that if I want to sum up all the elements of an array, I can do that, and the sum there is 45. But I can also optionally do this over a given axis. So I can, for example, sum over axis 0, so sum over all the rows and get a sum for each column, and that's represented in this result. Or I can sum over axis 1 and then get a sum for each row. And there are other kinds of aggregating operations. I can calculate the mean for each row or the standard deviation for each column, and so on and so forth. And so these are very useful, again, when you might have some data in a multi-dimensional array, but you need to do some computation that reduces that along one or more dimensions, and this provides useful functionality for that. And then we can combine these various pieces that I've been showing to sort of carry out more elaborate kind of operations. So one thing that you might do in a scientific computation, say if you were solving a partial differential equation, a diffusion equation or something, is you might have data stored in a 2D array, and you'd want to calculate what's known as a finite difference Laplacian. Sorry, I've got a couple more questions here. What if the arrays don't have the same size? Will it show an error? Yes, that you will. If you try adding two arrays of different sizes, you'll get an error saying you can't do that. And it's important to use, if you're writing code you want to be robust and you're not sure whether or not you're always going to have arrays of the same size, then you might want to use try except statements to deal with that. Right, and as Chris noted, unless it decides to broadcast a small array, that there are elements and aspects in which it does make sense, in fact, to sort of have things of different shapes depending on the operation, and this is what this broadcasting operation is about. That there's sort of internal broadcasting that NumPy does in certain cases, and then in fact there's a mechanism for you to kind of control that more explicitly. I was describing this finite difference Laplacian, so I might do something like this. If I have a 2D array, I might want to loop over all the elements of the array, and at every cell, I might want to, for example, grab the values of the neighboring cells and add them up, and then subtract off 4 times the value of the center cell. This is what's known as a stencil for this finite difference approximation to a Laplacian operator. And this is what this code that I've sketched out here is what you would typically think of when you do this. You loop over I and j, and you grab the neighboring elements and do that operation. But instead, you can actually do this computation all at once by generating shifted copies of the array. So if I create 4 additional copies of this array where I shift one row to the right, 1 row to the left, one column down, 1 column up, or however those words fit together, I can then basically bring into registry the original array plus all these shifted copies, and that's what's sketched out in this function at the bottom, that I can basically use slicing to create 4 shifted copies of the array and then subtract off 4 times the original array, and I can run that. And then if I were to run this on a big array, I can time things again. And so, for example, this function that I wrote using the shifted arrays takes 4.94 milliseconds on average. And if I were to write out, do the explicit loop, it'll churn for a little bit, and it takes 575 milliseconds. So, we can do another computation here, 575 divided by 4.94. And that's 116 times faster. So it's not quite we don't get quite the same speed up that we saw with the simple array operation. And one of the reasons for that probably is due to the fact, this question we just had a moment ago, sorry, I'm trying to go backwards, is that these array operations are binary. So every time I add these 2 arrays here, it creates a temporary array, which is the sum of those, and then it might add this third one and add it to that sum, creates another temporary array, creates another temporary array. So there are lots of temporary arrays that are getting created on the fly and then being deallocated in order to produce this final result. But that temporary array creation, even though it's very efficient to express that, it does introduce a little bit of a performance penalty, and sometimes that can be an important factor in performance. So, so the question about temporary arrays was very relevant there. Just a moment. I'm just going to sort of sum up with NumPy here. I've only showed you a few of the NumPy features. If you're doing any linear algebra, you certainly want to be able to make use of all of the support that's part of NumPy for that. There are a lot of exotic array broadcasting operations that let you, as we were sort of discussing, operate on arrays of different but compatible shapes in a variety of ways. And then there are a lot of different functions that allow you to filter and process data in a compact manner without having to sort of write out these for loops. And then various other kinds of derived arrays, masked arrays, and structured arrays and things. So I certainly encourage you, if you're interested in using NumPy, to consult the documentation, which describes this in a lot more detail. I'm going to move on now to SciPy, which is short for Scientific Python, and this sits on top of NumPy, and it wraps many kind of existing numerical routines that had been written over a number of years typically in C and Fortran, but that then provide convenient Python interfaces. And this provides routines for a lot of different kinds of operations that we'll look at a bit. And there's sort of a common theme in that these are engineered. The functions that are provided by SciPy are kind of generic, and that you can then customize the use of those functions for any particular problem by writing kind of user-defined Python functions that we'll look at. So SciPy consists of a number of different sub-packages that provide different kinds of functionality. And I'm going to focus on two of them today, the integrate and optimize packages, but depending on what you're working with, you might want to dive into some of these other pieces. And to motivate this, I'm just going to develop a kind of a simple problem example, example problem from infectious disease dynamics modeling, which you may have seen some of during these past few years. So the model I'm looking at here is what's known as an SIRS infection model. It's a compartmental model that I won't go into all the details in the math here, but that describes the fraction of a population that is either susceptible to infection and is actively infected and therefore can infect others, or is recovered and then is immune and cannot become infected. And then there are a series of transitions among states and an infection reaction, a recovery reaction. And in this case, unlike an SIR model, I'm actually building in a waning immunity. So instead of having lifelong immunity, in these SIRS models, you get a loss of immunity and therefore hosts return to this susceptible state. And so if you put all these things together, you can form a model which consists of a set of coupled ordinary differential equations for the S, the I, and the R compartments. And typically we treat this as an initial value problem in which we have some initial condition at some initial time, and we want to integrate it forward in time from that initial condition. And in SciPy, as well as in lots of other languages, there are packages that provide support for integrating these kinds of equations, and they typically all require writing the ODE in kind of this in this canonical form. So we have some vector of state variables y, and we have to specify the right-hand side of this differential equation encoded in some function f, which is potentially a function of time of the state variables and some vector of parameters. And so for this SIRS model, the state vector y is just these three components, S and I and R. The parameters, which I didn't mention, but are beta, gamma, and rho, are the rates for the infection, the recovery, and the waning immunity. And then this function f, which has really sort of all the action in it, is the thing that returns to the right-hand side. So it's just this three-component list or array describing how the S, the I's, and the R's change in time. And we can encode this all in Python and SciPy. So the key function we're going to use to integrate this differential equation is the solve IVP, so initial value problem. Solve the initial value problem from SciPy integrate from that submodule, and I can set some parameters. And you know, the key action here is to define this function f, this right-hand side that I'm calling SIRS, which takes t, the time, the state vector, and the parameter vector, and I can unpack those and write out these equations and return that list. And then I've written another function here that just lets me start from some initial condition where I have just a little bit of an infection in a susceptible population and evolves that forward in time for some amount of time. So I can run this all by and again, the key function to do the integration is this solve IVP. I pass in the function, then encodes the right-hand side. I say what time interval I want to integrate on. I give it my initial condition, why not, my additional arguments to the function, which are this parameter vector p, and then the times that I want to return the solution on. And when I execute this, I see that this thing returns. It successfully reached the end of the integration interval. The key elements that are returned here as part of this object output are the time points on which I've asked for the solution, and even more importantly, the state vector y, which is this 3 by n array. So this is a NumPy array, a 3 by n NumPy array that contains the values of the state variables at each of those time points. And it tells us additional things. So for example, it evaluated this right-hand side function 128 times in the process of producing that output. So if I want, I can take that data, and again, I'm not sort of focusing so much on the data visualization here, but I can use matplotlib to plot out these trajectories in time. I start with some population that's almost entirely susceptible, but then I get an infection, I get a burst of infection, and then eventually this system all settles down into a steady state where there's actually a non-zero amount of endemic infection in the population because of this process of losing immunity and having hosts return to the susceptible state. I'll just quickly, I mean, so I have this set of equations which I integrated. I treated as a set of differential equations which I integrated in time, but I might actually just be interested in finding these steady state solutions when at long times when nothing is changing. And in fact, there's a different function in the SciPy.optimize function that lets me essentially do root finding. So what I can do is encode a function f such that I want to find the value y star, such that all the components of f are 0. And essentially, that's what I've done here. I'm just using my previously defined right-hand side function, but then I can run this through, compute the steady state values, and those are plotted along with the trajectory with these black dots. So what this did is it didn't integrate the system forward in time. It just found the roots of this function such that when I started from some initial guess, it converged to the steady state values of Si and R. This is a kind of overkill for this particular example because you could actually algebraically just work out what the steady state solution is, but for more complicated problems, that can be a useful technique. Similarly, I might have the model, but I don't know the values of the parameters, and I want to estimate them by fitting the model to the data. Maybe I've got daily infection data. And I do this basically by essentially minimizing a loss function or an error function. So for any value of parameters p, I get some trajectory through y through time, and I can, for example, try to minimize a least squares cost function or a loss function by minimizing the deviation of the model predictions from these data that I've measured or that I've acquired. I just made up some fake data here by taking the trajectory and adding some noise to it, but this might be daily infection data that we get through a public health department or something. And essentially what I want to do is minimize this least squares error by finding an optimal set of parameters. And just the same way that in the the process of integrating a differential equation involves encoding the right-hand side of that equation, the process of root finding involves encoding a function that we want to find roots of. In this case, we need to specify what this cost function is, and we use this minimize function from the SciPy.optimize package. So for any parameter set of parameter values P, I can integrate my differential equation forward in time, and then I can compute using the NumPy.sum. I can compute this sum of squares error, and then I can start from some initial guess for the parameters. Maybe this is based on previous experience, and I can execute this optimization procedure. And again, so this then terminates. It finds an optimal set of parameters that minimizes this error function, and in fact, we can go ahead and plot that alongside the data. So the black dots are the data that I was fitting to. The blue dashed line is my initial guess, which didn't do a very good job of fitting the data. But then through iterating many times, I forgot to mention, if we can look at this, that it evaluated this cost function 225 times in the process of going from my initial guess to the best fit. And then the red line is the best fit set of values for that it determined through this optimization procedure. So again, there's a lot of very useful functionality encoded in different sub packages in SciPy that lets you take a basic problem and then investigate different aspects of it using different algorithms. So just as a sort of a recap there with SciPy, SciPy provides these consistent and convenient interfaces to a wide variety of different tools and algorithms, and organizing these sub packages, and then it uses NumPy arrays really as kind of this common substrate for storing and manipulating a lot of this kind of data. So I'm going to move on now to the last sort of main chapter of the talk here, which is this Pandas package, and I'm going to focus mostly sort of on kind of on these data frames that Pandas provides support for. So data frames and series are new data structures that are defined in Pandas. Again, they're not part of Python, they're not part of NumPy, but these are useful for dealing with tabular data, such as you'd find, say, in spreadsheets. And these are very similar if you've done things in R, for example, you work with data frames, and these are conceptually very similar. And Pandas uses NumPy underneath for much of the data processing. So Pandas provides support for reading from CSV or Excel files, or for connecting to SQL databases and getting data tables based on SQL queries that you can issue. It's also very useful in dealing with missing data, which often is the case in these kinds of data sets. There's support for adding new columns derived from existing columns, for grouping subsets of data in various ways that we'll look at, and then a lot of useful functionality for concatenating and joining and merging multiple data frames. And the basic anatomy of a data frame is sketched here, it borrows a lot of in fact, uses NumPy underneath to store each of the data in each of the columns, and then uses some of the same terminology. So we have axes. So axis equals 0 are the rows of this data table. Axis equal 1 are the columns. Unlike in a NumPy array, we now actually have labels on these things too. So we have an index, which by default is just an increasing set of integers, but it could be some other label you choose to apply. And then we have labels for the columns as well. And then importantly, whereas a NumPy array is homogeneous in type, obviously in a data table, you can have different types in each of the columns. And so there's a D type associated with each column that can be things like date times or string objects or floats or ints or what have you. But Pandas builds on top of NumPy by both internally by using NumPy arrays to store the data, and then using the terminology to provide an interface. So just as there was sort of a conventional shorthand for importing NumPy, there's a conventional shorthand for importing Pandas as PD. In this case, I'm going to import a data set. It's not about infectious diseases or scientific computing necessarily, but is some baseball data. So the baseball data bank stores all the sort of the historical records of Major League Baseball throughout its history. And the batting CSV file is one of 27 different files that store some of that data. And I've just read the one of them, but all of these are available at the Baseball Data Bank. And when I read this in, I basically get I get this data frame with more than 112,000 rows, where each row is an individual player in a particular year, and then all of their batting statistics, all of their hitting statistics for that year, and that aggregates up to this total. I can, for example, get a useful summary of the information in this data frame with this info method. And again, I see that there are 22 different statistics, 22 different columns associated with each of these player year combinations, and those are of different types depending on the data. One useful thing is to be able to add derived data, and this, in fact, you can see. So, for example, in this data set that I just had, there was information about the total number of hits that a player has, as well as the 2 base hits, the 3 base hits, and the home runs, which are 4 base hits. But it doesn't actually include information about the 1 base hits, the singles, and that's because that's sort of redundant information. Once you have the total and the 2s, the 3s, and the 4s, you can in fact derive it, and so we can in fact do that. And this just uses the same kind of list style indexing that we were looking at previously, except now because the columns have labels, we can index based on column names, not just on integer indices. And so now, once I've done this, I am essentially added a new column at the end here, which is the 1 base hit. So for each row, it's done this computation and then produced an entry there for each row in the table, and that can be useful for something I want to do with that. I can aggregate the data in different ways. So in the same way that I was able to sum up NumPy arrays, I can sum up data frames along a particular axis. So this operation, for example, will sum up over all it'll sum up over all the rows on axis equals 0. So it basically tells me the total number of each type of these different hitting events over the entire history of Major League Baseball. And maybe that's a useful thing, or maybe I want to break that down in some more detail. I can filter data in different ways using some of the same kinds of techniques we saw before. So if I wanted to get a list, for example, of all the seasons in which a player hit at least 50 home runs, I could use this logical operation first to do filtering on the home run column being greater than or equal to 50, and then I could filter out that subset. And so when I do that, I get this list of players in particular years who hit at least 50 home runs in a season. And if you actually look at this in detail, you see that more than half of these were within the last 30 years, as there's, for various reasons, been a big spike in home run hitting in baseball. One of the things about these data tables is that there's a lot of substructure that we often want to be able to access and group in different ways. And these are support for some of this is provided in Pandas by what is known as a group by method on data frames. And this supports what are known kind of generically as split, apply, combine operations. So I can split a data frame into subgroups based upon the identity of a particular key or some other criterion. Maybe I want to cut based on different values of some field. I can then apply, and after I've done the split, I apply some aggregating function to each of the subgroups, and then I can combine the aggregated information back into a single data frame. So for example, if I want to know the total number of each type of event for each year, I can group by year and then sum things up. So this would give me information about, on a per one row for each year throughout the history of Major League Baseball, the sum of each of the different hitting events per year. And I could look at historical trends, for example, that way. I might be interested in players instead. And so I might want to, for example, generate the lifetime batting statistics for each player. And so I can do that by grouping over the player ID and summing things up. And then if I look at the results here, now I have a row for each of the more than 20,000 people who've played in Major League Baseball. what their lifetime statistics are in each of these different categories. I can in the same way that I was able to plot up data from NumPy arrays using matplotlib. It turns out that Pandas uses matplotlib and supports various kinds of plotting methods. So if I wanted to look at historical trends of, for example, both the change over time of the number of home runs in blue and then there were strikeouts in orange, I can plot those conveniently. Or I might be interested in plotting them against each other. And we see that, in fact, that home runs and strikeouts historically have been very strongly correlated. If I want to examine this correlation among different variables in more detail, there's a convenient method here, the core method. And so this then essentially computes the Pearson, in this case, the Pearson correlation between all different pairs of events. And so, for example, if I'm interested in this relationship between home runs and strikeouts, I see that they have a Pearson correlation here of greater than 0.96, as sort of revealed in this plot here. Pandas also interfaces nicely with other modules such as stats models, which lets us do various kinds of statistical modeling. So we might want to do a regression of this home run and strikeout data, in this case, just using an ordinary least squares. And when I set up this model and do this fit, I get this detailed summary, statistical summary, which is similar to what you might find in R or SAS or something that describes the results of this least squares fit, but then also importantly sort of reveals these coefficients, both the intercept and the slope of this least squares fit that I did. And if I want, I can make a plot now of this best fit line to the data using the graphics within the stats models package. So I've sort of gotten to the end of talking about pandas, and I just want to sort of wrap up a bit by sort of talking about things a bit about the way all these different pieces fit together. So I hope I showed you how with this core Python language, and then importantly, the Python C API that allows us to build extension modules, we can build a variety of different kinds of libraries and tools that allow us to combine the expressiveness of the Python language itself with the performance of compiled code that we get by building these extension modules. So we can build both sort of compact array notations as well as performant ones using NumPy, which then feeds up into things like SciPy and Pandas and stats models and the rest of the things in this suite. I showed you a little bit of data visualization here, but as I said, in next month there'll be a more detailed talk on sort of digging into these packages in some more detail. And then a lot of these things flow into a whole sort of an ecosystem for doing machine learning that is really an entirely separate talk in its own. scikit-learn, TensorFlow, PyTorch, all of these things make a lot of use of data stored in NumPy arrays or Pandas data frames. Some of them work directly with those data. In the case of things like TensorFlow and PyTorch, interestingly, they end up having to define a slightly different kind of internal representation of arrays. And these are arrays for storing data and the parameters in neural network models and things. But in order to do efficient computations in neural networks, they need to be able to also compute derivatives of operations. So this is used for backpropagation for training neural network models to data. And so even though they sort of implement a lot of the same kind of API that NumPy provides, they actually develop internally their own array libraries that implement what's known as automatic differentiation that lets for efficient parameter training in those kinds of neural network models with very large models and very large data sets. I hope I've given you a sense of what this ecosystem looks like and sort of at least some of the key functionalities of a few of these packages are, as well as the way that some of the pieces fit together to allow us to build up complicated computations.